hypothesis testing for the variance or standard deviation. So for the test score, it's not the z-test, it's not t-test, but chi-squared test. And the formula is shown as n minus 1, which is the degrees of freedom, if you will, and the s squared over the sigma squared. So what are the assumptions for the chi-squared test? Number one, the sample must be randomly selected, which is really common to all of statistics. The sample must be representative always. Second, the population must be normally distributed for the variable under study. Okay, normal distribution still. And the last is the observations must be independent of one another. Find the area under the chi-square distribution. Use table G, appendix C. There are three cases to consider. One, finding the chi-square critical value for a specific alpha when the hypothesis test is right-tailed. For a specific alpha when hypothesis test is left-tailed, and for a specific alpha when the hypothesis test is true-tailed. All right, let's do some problems. Okay, so for the first problem, find the critical chi-square value for 15 degrees of freedom when alpha is 0.05 and the test is right-tailed. So remember, when it comes to chi-squared distribution or distribution of variance or distribution of standard deviation, the curve is not normal. Okay, so it is skewed to the right. Okay, so for the right tail, which it has 0.05, so you can't really locate the centers now. So let's look at the table G. Table G 0.05. So let's look at 0.05 here. And degrees of freedom to be 15. So 15 by here at the top. So 24.996. Therefore, the chi-squared is 24.996. You can also verify now if the chi-squared is most likely to be correct because, of course, right-tailed, your chi-squared value must be bigger because it is to the right. Okay. When you're looking for the value to the left, then it must not be around 24, 20, or 15. Next example, find the critical chi-squared value for 10 degrees of freedom when alpha is 0.05 and the test is left-tailed. Okay, so even though the alpha is 0.05, we cannot use 0.05 in table G because it is left-tailed. So the alpha is actually here. So I think the best way to check or to verify is not, number one, not to be confused with the left with the alpha. Okay, you just have to concentrate on whether it is right-tailed or left-tailed, and of course the absolute value of the chi-squared. Let's try to check on the table G. So the alpha is 0.05, yes, and the test is left-tailed, and the degrees of freedom is 10. So degrees of freedom is 10. So if you use 5 or 0.05, you will end up having a value of 18.307. Again, that is large. So that is not likely to be right-tailed. So since it is left-tailed, even though the alpha is 0.05, you have to subtract it from 100 or 1. So we should look for 0.95. So 10, then 0.95 here. So that's 3.940. So the chi-squared is 3.940. Right? It makes sense because it is to the left of the distribution. Last, find the critical chi-square values for 22 degrees of freedom when alpha is 0.05 and two-tailed test is conducted. Okay, so I have no enough space here at the bottom. So this is 0.05, therefore this is 0.025. Always remember that when your curve is two-tailed, the alpha must be divided by 2. This is 0.025. So 22 degrees of freedom. First, let's look at the right. 0.025. 22. 22, then 0.025. So this is it. That's 36781. 36781. Okay, this is left, this is right. For the left tail, 0.025, you have to subtract it from 1. So that's 0.975 for the same degrees of freedom. 22. 0.975, so this is it. 10.982. Yep. So the left is 10.982. 10.980. Okay, so that's how you find the chi-squared value, right, left, or two-tailed. Now, for the actual sample problem, let's have this one. An instructor wishes to see whether the variation in scores of the 22 students in her class is less than variance of the population. Variance of the class is 198. Is there enough evidence to support the claim that the variation of the students is less than the population variance, which is 2 to 5? Okay, so first things first. Um, variance is squared is equals to 2 to 5. The alternative is that the variance is less than 2 to 5, which is based on sample is 198. Alright, so for the price test, it's n minus 1 s squared sigma squared. It is 23 minus 1 times the sample standard, the variance of the class. So this is the s squared, okay, because the class is the sample variation. It is the sample. So it's 188 divided by the 225. So that's 22 times 108 divided by 225. That's 19.36. Okay, so we have now the chi-squared test value. What is the question? Is there enough evidence to support the claim that the variation of the students of 23 students is less than the population? At 0.05, less than, so let's draw it. This is the 0.05. Okay, degrees of freedom is 22. So let's look at the table G, 22 and 0.05. So since it is on the left, we should look for 0.95. 0.95 is here, and 22. That's 12.338. What is 12.338? That's the critical value. 12.338. And the chi-squared is in here. So there's not enough evidence to support the alternative. Therefore, accept the null hypothesis. But that is using the traditional method. Okay, let's take a look at this. Approximate p-values for the chi-squared test can be found by using table G in Appendix C. The procedure is somewhat more complicated than the previous procedures for finding p-values for the z and p test, since the chi-square distribution is not exactly symmetric, correct? And chi-squared values cannot be negative, as we did for the t-test. We will determine an interval for p-value based on the table. Okay, so let's not discuss this part anymore about how to find the p-value or how to do hypothesis testing using the p-value method on variance and standard deviation because it's a little bit complicated and confusing. So it might confuse you. So only the p-value method for z-test, t-test, and proportion. So let's skip this one. Okay, so that's all. If you have any questions, please don't be shy to ask questions. So thank you.